All right, before we get started with class today, I thought I'd mention this preparing you for your ACS examination in general chemistry, the official guide. So the first Gen Chem final will be the ACS final, December 5th, I think 10 a.m., is that right?
Mm-hmm. Yeah, sure, sounds good.
And this is the guidebook for it. I have a copy that I keep for myself, so if you come to office hours, you can kind of work through some problems from this. There's also one at the reserve desk at the library. So if you go to the library, ask for the reserve desk. If there's particular topics you want to try to work through problems on, take this book, photocopy some pages out of it. If I understand right, you guys automatically have $5 of copying on your ID card per semester or whatever it is. So you should be able to make some copies if you want, and that would give you some problems to practice through. The ACS final is all multiple choice, so this is a good place to go. You can only check it out for 2 hours because there's only one copy there. So if you go to check it out and someone else has it, they're probably right in that area in the library making copies of it. So don't check it out and try to work problems. Check it out, make copies, and then work problems on the copies.
Matt, can you buy it, like online or anything?
I have no idea. Can you check and post to Blackboard discussions under logistics, post exam 3?
Yeah.
If you can buy this. It's a good question.
Amazon.
Okay, it is on Amazon.
Isn't
That's
there
fine.
one free practice question?
I think you can Google ACS practice questions as well. I think you should be able to kind of see how everything fits together by doing the practice problems. Yeah, $8. Perfect. All right, those copies are all going to be bought in the next 2 minutes. Yeah, Joe.
What's that book called?
It is called Preparing for Your ACS Examination in General Chemistry, the official guide. I will leave it up here so you guys can come check it out. All right, so we have 5 classes left together. Makes me sad. But hopefully I'll have a number of you next semester. The Super Gel, Super Coffee. We will spend those 5 days focusing mostly on thermo. We're going to finish talking about how to calculate the amount of energy released, delta H of a reaction, today and probably Friday. And then when we come back, we'll spend a couple days reflecting back to your lab that you did with transfer of heat from a chemical reaction, measuring the change in temperature of water, that kind of stuff. That should get us pretty close to the end of the semester. I have office hours today right after class for an hour, and then tomorrow from 1 to 2-ish, 2:30, whatever, if people stick around. Can I get a show of hands how many people might be at each so we can decide what location? For today, 11 o'clock to 12-ish, 12:30, whatever we do. Okay, so maybe 2 people, so we'll do Science Lab 273 today. What about tomorrow, 1 to 2:30-ish? All right, and we can call that exam review and kind of do the same thing. So we'll do that in ETAS 125, right over here. All right, so let's get into it. Go ahead and look at the first question on your worksheet. Try to figure out which 3 of these you think releases more energy from the reaction of burning 1 gallon of gasoline when you're in your car.
I'd like to put my thought, my one question for the day
Okay.
into this.
You're gonna preemptively call that.
Yeah.
Is it a Prius?
No.
Pretty sure Prius gets more than 27.9 miles per gallon.
Could be a
You get the idea.
Get up. You want to stand up?
No.
All right, a couple more seconds. We have 35 responses. We probably have about 40 people here today. So we have a split of responses. Go ahead and talk to your neighbor. And might there be another answer that you would like to add to this? Go ahead and talk to your neighbor. and try to decide which one of these you prefer, and then if there's another answer you might want to add.
I already know.
And if you want to add an answer, click D, and then we can hear what those answers might be. It should be similar by here. All right, a couple more seconds. If you're going to change your answer after your discussion, go ahead and change it. Otherwise, leave your answer as it was. It's still open. All right, now we have 4 answers with everyone choosing a decent number of them. Jackson, what are your thoughts on this?
Okay, number one thing. Gasoline, when you burn something, it doesn't really matter how the energy from the burning is used. It's going to release the same amount of energy, whether the car is parked and sitting idle, or whether it's driving on the highway, because of the fact that gasoline has a set amount of energy whenever you burn it complete with oxygen in the air, which is how you're burning it.
So answer D.
So it has
They're
to
all
be,
the same.
They're all the same.
Nice. Kind of a trick question. We're kind of not. Right? So I want us thinking about, does it matter what is done with the energy released? That doesn't tell us how much energy was released. So this question is about how much energy is released from the reaction. What dictates how much energy is released from a reaction? What is it that dictates how much energy is released from a reaction? Go ahead and talk to your neighbor for a second. What dictates the amount of energy released from a reaction?
I'm going to say the amount of energy from the reaction either absorbed, at least from the reaction, is basically what happens to the bonds. What happens to the bonds. If they form in a way that results in a more stable molecule, it releases the energy from the less stable reactants into the more stable products. Vice versa.
Alright, can I hear from a new voice? What is it that dictates the amount of energy that's released or absorbed from a reaction? What was that, Joe?
Is it how much is put in? The input,
Yes. Explain that a little bit more. What do you mean the input of energy?
You're only going to get so much energy from the gasoline depending on how much gasoline you put in it.
Oh, how much gasoline? So you're saying how much reactant you have?
Yeah.
Okay, yeah, that's absolutely part of it. Amber?
The bonds within each molecule of gas.
Okay, that's part of it as well. What else do we need to know besides the bonds in the gasoline? Matt?
The bonds in the products.
Because if we are burning something, it means that we're breaking apart. So in this case, we have octane. We can kind of assume all gasoline is octane. And oxygen molecules. Obviously, we have to think about the stoichiometry of each of those. It requires, like Joey said, a certain amount of energy to break apart all the bonds in our reactants. But then after we do that, we form a whole bunch of new bonds. And so, what are the products we make in a combustion reaction with octane? CO2 in the water. Certain number of each of those, and every bond that we form releases a certain amount of energy. So what we're talking about is what is the difference between the amount of energy required to break the bonds, the amount of energy released to form the bonds. That's what dictates how much energy is released or absorbed in the course of a reaction. Questions? So we have to think about the whole picture. We can't just think about reactants. We can't just think about products. And that diagram is going to be true for, in this case, it would probably be a mole of gasoline. If we have a gallon, that might not be the exact number that delta H is there.
So, what was the answer? Sorry, like, for,
So the answer for the first question that I just asked was that they all release an equal amount of energy. And then let's talk about, use those same three options to answer the second question. Which of these scenarios releases more energy in the form of heat?
the question you wrote, sorry. What dictates the amount of energy?
The bond's broken and the bond's formed. So go ahead and talk to your neighbor, try to answer the second question here. Which of the above scenarios releases more energy in the form of heat? It might be useful to think about what other forms of energy can be released from a reaction. We have almost an equal split. Talk to your neighbor. Try to figure out logically which one of these three ways of burning that gallon of gas is going to release more energy in the form of heat, specifically heat.
Well, it starts to feel like that.
What are the two ways that heat, that energy can be transferred from a chemical reaction? Two different ways. Tyler? Okay, so then maybe we go a bigger picture, broader. Energy being transferred in the form of heat, and what's the other one?
Work.
What's that?
Work.
Work. Work, what does work mean? Movement of something with mass. So if we're able to move something that has mass, then that's energy being used to do work. Alright, so Sam was saying when our car drives, there's friction on the ground, there's wind resistance around the car. Wind resistance is that energy being used to push gas molecules out of the way. What about the movement of the car itself? Is that heat or is that work? That's work, right? It's taking something with a lot of mass and moving it. So those chemical bonds that are being broken and reformed, that transfer of energy is not just a transfer of heat, it is also transferring in the form of work.
So basically you're saying the car sitting there idle does less work than driving.
And at first you might think it does no work, but why can't we say it does no work?
Because you get all the pistons going, not even enough.
Yeah, so the pistons have weight, pistons are moving, they're not being used to engage the wheels and move the whole car, but there's a little bit of mass that's moving relative to what you'd have if you drive a car. So if you get out in your car, you turn it on in the morning to warm it up, you're taking all the chemical energy that's being generated from the breaking of these bonds and the forming of these, and using all that to only generate heat. If you're going somewhere, what do you think the ratio is? If we're driving, so in scenario B, for driving that far, what percentage of the energy do you think we're actually using for work? Talk to your neighbor. What would you guess? What percentage of the energy that comes out of this chemical reaction do you think is being put into the work to drive the car?
I already know the.
You already had your one.
I know, but I already know the answer to this. Sorry, I had to.
All right, so let's do this a bit of a different way. We're going to have your hands raised if you think it's greater than this percent. I'm going to call it efficiency. Efficiency is the percentage that goes towards work out of the total energy lost, okay? So do you think it's greater than 5% of the energy transfer that's going to work in your car? Greater than 5%. What about greater than 10% of the energy transfer that's going to work instead of heat? 20%. 30%. 40%. 50. 60. 70. 80? Why did you put your hand down? Why is it not 100%?
I was thinking it was 100%, but everyone else put their hand down.
Okay, so when we're driving our car, we turn on the heater. Where's that heat coming from? Excess heat from the engine. And so when we look at the average car, granted it changes a lot, but the average car only gets about 20% efficient. That means that about 20% of the energy that is released from the breaking and forming of these bonds is used to do work. The rest of it, where does it go?
It's lost.
In the form of heat. What about our bodies? How efficient do you think we are? We metabolize food, right? We don't give off heat like a car, do we? So it turns out that humans are actually only about 20% efficient as well. It's pretty sad. So when you run, when you exercise, and you consume, you break certain chemical bonds to reform new ones, we basically, if you simplify it, we basically do combustion, but with many steps in between. Taking glucose and converting it into CO2 and water. That process we're not very efficient at. We actually lose a lot of heat in the process, and that's why we sweat to cool it down. There's a lot of friction and a lot of other things, so we lose a lot of our energy in the form of heat. So when we're talking about energy, in chemistry we're going to define that extremely simply. We're going to define it simply as the ability to do work or transfer heat. And as Gail was talking about, if you take an object that has mass and we move it, that's what we call work. And heat raises the kinetic energy of a substance. And we can measure that by the increase in the temperature. So this is kind of the simplest equation that you'll see that connects these two to each other. That the total energy of a system, usually it's more accurately drawn as the change in energy, delta E, is equal to how much work is done, W, and how much heat is transferred, Q. Do any of those variables look familiar to you? You guys' lab that you did?
Yeah.
You were measuring just how much heat was released, Q. Calorimetry? No? Have you guys done your calorimetry lab yet?
I have.
All right, so that's what we're going to talk about after Thanksgiving, is we're going to focus more on the heat transfer measured in a specific reaction that you guys did in your lab. I'm going to show you guys. If you think about energy being transferred to move mass, do you ever think about a battery and how that moves mass? Let me show you guys this little video here. So you take a battery, put a magnet on the bottom, and then put copper wire. That's chemical energy from a battery being used to do work. Physics is a weird thing. and you guys have already been working with this. The unit that we're going to be talking about most, the standard unit, is a joule, but calorie is also another version of measuring energy. You guys have heard calories before? All right.
Oh, that's bad.
Alright, see you later.
Our projector might take a second to warm back up.
I was like, oh, we're getting out early.
There's plenty we can do without energy. So where do you guys normally hear of calories? So if we look at the back of the bag that Jackson just held up, and it says a certain number of calories on that. So this bag says 350 calories per pack. What does that mean?
I think it's for crackers.
What does that mean? What does 350 calories per pack mean? Talk to your neighbor. In chemistry terms, how do we describe what that 350 calories is? Goldfish are energy. Right, not true.
Well, they're not literally energy. They contain energy. There you go. Quite a lot of it at that. That's big C calorie. That's kilocalories.
All right, can I hear from a new group? How do we describe in chemical terms what is meant by the term calorie on your food? What do you mean by energy, sir? Energy what?
Is there energy in the food?
It gives you energy
How do we get energy from the food?
by eating.
Okay, and then after we eat the food, it doesn't just like explode and give us energy. So what happens? Say what? What does that mean? Chemically, what does that mean? We break bonds and form new ones. Alright, so that 350 calories is how much energy can be released if we consume that food, break down the molecules, rearrange those atoms into new molecules, the total transfer of energy from input of energy, release of energy, that's how much energy our bodies can get. And one thing to note is that just a second ago we said that calorie is a unit that's related. I think it's 1 calorie is 4.184 joules. This calorie is not the same calorie that's on your food bag. Your food bag is capital C, which is actually
Kilocalories.
1,000 calories, or a kilocalorie. So that means that if we want to figure out how many joules are in that bag, we would have to figure out a couple conversions. You can do that with your knowledge of conversion factors, correct? All right, I'm not quite sure why my laptop is still not projecting. Let's try unplug, replug. All right. We are at HDMI input. Okay. So what I want us to do next we're going to be working on problems, so it's going to end up being fine. So I wanted to read you one quote before we went on to talk more about thermo. It's by one of my favorite physicists, Richard Feynman.
Oh, yes, that dude.
He said, "There's a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called conservation of energy." So the point of that is that if we're thinking about energy being absorbed and released in the process of doing a chemical reaction, all of that energy has to be accounted for. It's either going to be released in the form of heat or it's going to be doing some work. When we think of work, we usually think of larger objects with mass. We think about moving this rock, right? That requires some work. So what I want to start and think about is that you can actually think about molecular work as well. So if you have a water molecule, the shape of the water molecule, I don't know why there's so few chalk, is like this, because it's a tetrahedral electron pair geometry. Molecular shape is bent because all the groups are repelling each other. So sometimes energy gets absorbed by molecules and does work by moving objects with mass. We can have fluctuation of those if this molecule absorbs energy. Atoms have mass, that mass moves, that still counts. We can have the movement of water molecules, those speed up, that's also transfer of energy in the form of work.
Isn't the former, like the first process you said, like the molecules of water vibrating, in a sense, how microwaves cook your food?
Absolutely. So microwaves cook your food by converting light energy, microwaves, into vibrational energy, and then that creates friction when they slow down, which heats up your food. So just to read them out loud, since I'm gonna have to go play with the projector in a second. There's no. Let's go ahead and talk through questions 12, 13, and then hopefully you guys are working on 14. So question 12, what products are formed when you combust the fatty acid methyl ester? Can I get a hand raise? Go ahead, Christine.
Carbon dioxide and water.
Great. Are there any other reactants we need for this reaction? Maybe I should write out, instead of fatty acid methyl ester, we write out formula. How do we know that the products formed are going to be CO2 and water? Why are there no sulfur or nitrogen containing compounds in the products?
None in the reaction.
There's none in the reactants. It's a combustion reaction, which means combining a fuel with oxygen. There's only carbon, hydrogen, and oxygen, which means our products are only going to have carbon, hydrogen, and oxygen. And we assume in this class that the only products that come from carbon are CO2, hydrogen, or water. That's not always completely accurate. We know that if you have a fire in your house, you can get carbon monoxide poisoning, so you can get other products. So we're simplifying it for the sake of our class today. All right. Did anyone balance this equation?
Yes.
All right. What did you get?
So 2702, 19 CO3, and 18 H2.
Does that line up with what you guys got? I see some people saying yes, some people saying no.
You actually need two of those things because Because if you take a look, there are 34 hydrogens in the...
30, huh?
Oh, never mind. I screwed that up. I am done.
Alright. Aaron?
I screwed the formula up. Thanks.
I'm sorry, I couldn't hear you. Say again?
I just said 9 to 18H2O because the easiest way to balance it is to start with hydrogen because you have it on one side and those would be emissions. So to get 36, you need 18 for water, and then you add up your O2.
That's 36 on the other side.
There's 36 H2.
Because there's two H's, you multiply by 18 is 36.
And then you add up your O2 on each side.
So for...
You get,
So I'm going to do carbon next because that's defined. 1, 2 plus 17 is 19 carbons. So we need 19 CO2s. And then after that, we would figure out the oxygens to balance them.
There's 36 hydrogens on the other side.
Oh, so we...
18 times 2. So 36.
Oh, yeah, sorry, I meant waters. Thanks. Good call. Silly mistake. Alright, so I think this equation is nice and balanced. So then if we're going to draw an energy diagram, an enthalpy diagram, without thinking about any of the calculations, is it going to look like this? Or are the products going to be higher than the reactants? How do we know? So which of these two diagrams do you think is most appropriate? Josh, what do you think?
I think it's going to be products are lower than reactants.
Why?
When you do calculating delta H and products minus reactants and look at the...
Whoa. Before we get into calculations, no math at all. Joey.
Never mind.
Taylor. Yeah, super simple. Use logic. It's an exothermic reaction. An exothermic reaction releases energy overall. That means delta H is going to be negative, which means that this is the way we're going to draw our enthalpy diagram. Great, Taylor.
Could we look at the number of bonds formed in the products?
It's going to be really difficult to look at the number of bonds formed because some are single bonds, some are double bonds, and those all have different enthalpy changes for each one. So I would stay away from that for a little bit before the logic version of it. If we know it releases heat, which most combustion reactions do, and this actually might be a problem, this is going to cover what I was just doing. I was just going to see if our projector is going to come on. But is that maybe?
Sounded like it was going.
We'll see if the screen turns on. All right. And then how do we figure out how much energy is transferred? I want you guys to go ahead and spend the next 3 or 4 minutes to try to calculate what delta H of the reaction is with the information that you have.
It was turned on. I saw HDMI and it's operating.
Yeah, but HDMI means it's not actually receiving signal. Unfortunately, that's what it was doing before I turned it all off and back on. All right.
Well, I got the right answer this time. I got negative 8,700.
All right, so my clicker is open. It's just going to show you basically this. But go ahead and click in what delta H is for this reaction once you get that. Ooh, and I did numeric. It should have been alphanumeric. Think about what the units would be for this answer. Please raise your hand if you want any help. Sam and I will be walking around.
Yes, Sam, walking around.
I screwed up the actual reaction loss, so there you go. Well, I guess we'll see who's right then. It's missing. I mean, it's okay to have he said that.
Jack. 5,000. 45,000.
Is it 40?
18 and 19. 45,000. Yeah, that's what I got.
That's not what I did. I basically took the, well, what I did is I took basically the same, should be the same answer. Yeah, exactly.
What did you get? The H was 9,000. So I would compare the approach. Really important to do that, and then see. Could be a reasonable answer, it could not.
All right, we have about 5 minutes left in class. So let's think about this. If we do this reaction, does it happen spontaneously? If we have biofuel sitting with oxygen in the air, does it spontaneously combust?
No.
So one term I'm going to introduce today is this idea of activation energy. And so we're going to be drawing a lot more of these diagrams probably second semester. But in order for our reactants to become products, we do have to put in some energy. Now it's not necessarily going to be the amount of energy required to break every single bond in our reactants. It's going to be less than that because some of the reactions happen with more intermediates that are more stable. But in this case, our activation energy is going to be a certain amount of energy that goes in. And then if we're really looking for, regardless of activation energy, we're looking for how much the change in energy was between reactants and products. So in order to, I'm going to take a look at these answers. I think I can do that while it's still running. So we have some answers that are all over the place. We have 79% of the class with an answer of negative 9,181 kilojoules per mole. Can I have someone who hasn't shared yet? How would we go about this? Because the first thing that I want to do, if I'm new to this, is I'm going to say that my reactants, delta H of the first half of this reaction is negative 22,495 plus negative 498. And then we're going to change the sign because it's an input of energy. So can I have someone tell me why that is not the appropriate input of energy required. Can I hear from a new voice? Deandra. So why does that matter? Why? Conceptually, molecularly, what's going on?
That's how much heat, or that's how much input energy is per mole of that.
Okay? And I want us, I guess the point that I'm trying to get at is that every O2 has 2 bonds. So if it requires 498 kilojoules to break apart a mole of these, well, we have 27 moles of double bonds that we need to break in order to go initiate this reaction. Okay? So times 27. And then on the product side, our delta H here, what do we have on that side? Kyle?
With the full number or the equation?
So what are the 2 things that we have here? What are our numbers?
It would be 19 times 1490.
Negative 1490
Yeah, plus 18 times negative 934.
times negative 934.
Yes.
And so this should give us how much energy is released when those atoms recombine in order to form our products. So if we go through those calculations, I've talked to a couple people throughout the last week and a half who say, is it products minus reactants, reactants minus products? I don't care. I want you looking at it. That's why the first thing we did is I said, which of these 2 diagrams is appropriate? And based off of that, our delta H should be negative. Right? So what I want you to do is I want you to find the difference between these 2, this one versus this one, and then we know it's a negative sign. All right? If you use logic, you're never going to go wrong in that calculation. You're never going to get the wrong sign.
So what's the answer?
So I think our delta H for this reaction is negative 9,000, what is it, 181 kilojoules per mole of what? Per mole of what? Is it per mole of oxygen? It's per 27 moles of oxygen, or per 1 mole of fatty acid methyl ester, or for every 19 moles of CO2 formed. So you could also report this as negative 9.181 megajoules per mole. All right, thanks for your patience with the tech, guys. Sorry it didn't quite work out. What's the other way we could do this, by the way, as you guys are walking out the door? If we knew how many O2 bonds we break, could you figure out how much energy that takes? If we figure out how many CH bonds, how many CC, how many CO bonds we break, we could add up all the bonds broken, all the bonds formed, but that's what that table summarizes for you. So I would much rather use delta HAC because that tells you about the whole molecule. All right, I'll be over in Science Lab 273 for the next hour and a bit if you want to come by and chat about some of these.